этих. Все понятно. Доктор, Маш, наука, профессор. Кузнецов, я говорю, нет, смотри, пер.
И вот так будет выше.
Да.
Потом можно будет обрезать. В принципе.
Нет, это можно, в принципе, вот так уменьшить.
Оно больше не станет, наверное. Оно больше не станет. Тут формат такой. Наверное.
Ну, наверное.
Это самое.
Ну пусть вот так будет.
Это, знаешь, Фока-Швингера, это продолжение, кто начинал это делать.
Так, давайте я попробую позвать в отделе
Он считается в одном деле
наших коллег.
до сих пор работа цитируется. И потом, по-моему, целый контакт.
Станислав, еще 2-3 минутки, ладно, я позову.
Да, конечно, не проблема, конечно.
А что там смысл они во внешнем поле по операции?
Ну, я не знаю, что они будут считать. Ну, я там разбирал, считал даже функции, перенумеровки, там во внешнем поле у него функция там своя получалась, а для чего там слабых магнитов. У него там целые всякие различные вещи. И там с точки зрения перенумеровок аккуратно.
Слушай, ну там же это вот такие вещи делали скалы в тюрьме.
Да, но они петли не читают. И потом у них по-моему, посильнее все-таки. А может быть и нет.
Я там
У них посильнее.
присутствие магнитного поля.
Хотя нет, у них не очень. Это потом посильнее. Ну, может быть. Может быть и они тоже. Потом могут и они, Михеев там и прочие, у них, Ярослав, они все, они больше все, они все его считают.
Нет, ну они там не
Ну, конечно, не прямо, но в таких.
А у нас будет это товарищество еще?
Да, хочет.
Добрый день.
Приветствую.
Привет. Вот Коля, наверное, лучше всех знает, чем оценки.
Коля?
Да. Ну ничего, они, так сказать, пока типа такое промежуточное решение, еще пока не выиграли нас. 8 июня следующий раунд. Но это, знаешь, это как вот лягушка наметила в огне.
А что же, а что ты?
Ну, один сказал,
Станислав, а у вас доклад на русском, да? И...
На русском, да.
А то у нас тут есть один иностранец.
Ну, просто в письме изначально на русском было указано.
Да. Ну, я не предполагал, что он появится, поэтому.
Немцы просто сказали, что мы вообще там.
Всюду вообще на
Нет, ну это следующий шаг,
Они 8 июня собираются обсуждать еще раз.
Да, но я говорю, это как вот медленно там, ну как вот первый этап, второй этап, третий, четвертый, здесь
Палец отрезать, потом всю руку. И так далее. А? Немцы? Не знаю.
Потому что на бейзе, на сферу.
ну они типа степ-бай.
Станислав, а вот вы сейчас слышите, как разговор идет где-то там, или плохо, да?
На фоне слышно, звука, но слышно.
Ну, может, она по-другому
Коллеги, чтобы задавать вопросы, лучше садитесь поближе.
Давайте, ладно. Какая жара, серая диаграмма.
Ну где там услуга?
Нет, я думаю, что у них это самое в значительной степени связано с тем, что действует генетическая память.
Это другая.
Ну, госпожа кандидат наук-то все-таки из восточника.
Ну и нет, генетическая память еще дальше туда.
Еще дальше, конечно. Но она же Кузнецовская была.
Они сравнивают себя с тем, что
Так.
сами
Коллеги, прозрачки у нас на русском, я вот не знаю, как нам поступить. У нас просто...
Мы еще не изучили.
Нет, по-русски у нас просто один есть коллега. Который пока не научился, да.
Если готов, Станислав.
Я просто его не предупреждал, я сам не знал, когда мы обсуждали.
Формула там.
Формула не в Африке.
Да, я понимаю. Станислав, а вы будете способны рассказать на английском ваш доклад?
Ну, давай попробуем.
А у нас есть один иностранец.
Здесь или?
Здесь. Okay, so let's start our seminar. Today we are going to welcome Stanislav Yablokov from Yaroslavl State University. He will tell us about modified Foka-Švingera method for finding exact solutions of propagator equations in the presence of magnetic field. The talk is based on his PhD thesis. So please, Stanislav.
Should I start? Okay, thank you. So once again, my name is Stanislav Yablokov, and my supervisor is Kuznecov Alexandr Vasilyevich. During these 4 years, during my PhD studies, we were working on the so-called modified Foka-Švingera approach, which is basically modification of the original Foka-Švingera method for finding propagators in external fields and in our general setups. And so let me present my results to you. In many cases, interesting discoveries happen on the intersection of different disciplines or even sciences. And the more those sciences are far away from each other, the more unexpected the results will be. And so one of such disciplines, particle astrophysics, combines in itself the most tiniest parts, like elementary particles, and the giant objects like stars. And so in astrophysical conditions, for example, when a magnetic field is present or with plasma, many processes are allowed, for example, photon decomposition into electron, positron, and many others. And so those processes might be important drivers of the observed astrophysical phenomena. When there are external fields, both the exact solutions of the corresponding field equations are modified, and also the respective propagators. So for example, in the case of magnetic field, in addition to the division of representations into momentum space and position space, we also have divisions driven by the parametrization due to magnetic field, either the proper time integral parametrization or Landau level decomposition. So let us briefly discuss the two main approaches to finding propagators. The first one is based on mechanical formalism and is basically could be described as sum over solutions. The second one comes from the path integral formalism, and results could be obtained for solving the so-called propagator equation, basically the same equation as the respective field equation, however, with the delta function on the right-hand side. And so let us briefly review the main steps for building propagators in mechanical schemes. So first of all, we have to find a general form of a solution. Next, if it so happens that we are interested in the propagator for a particle with spin of polarization, that the corresponding vectors should also be found or orthogonalized and normalized. And finally, we have to calculate the sum of the polarizations which occurs in the canonical quantization scheme. In contrast, when using the path integral formalism solving the corresponding propagator equation, we just have to find the general form by making basically a Fourier transform and solving the corresponding algebraic equation. So no need to compute polarization of spin vectors or orthogonalize and normalize them, neither to make the sum of the polarizations. But in this case, we implicitly assume that there is translational invariance. However, when we consider cases with external fields, we have to use the covariant derivative. And in this case, translational invariance in general is lost. So how do we solve this problem? Well, actually, let us go to chapter 1 and this problem with where translational invariance is lost was actually first solved in the so-called Foka-Švingera approach for providing propagators. In this chapter, we build the general form of this. In this chapter, using this original Foka-Švingera approach, we build the so-called modified approach with slightly changed computational scheme. And using both the original Foka-Švingera approach and the modified Foka-Švingera approach, we provide as an example the computation of the propagator for a scalar charged particle in constant magnetic field in momentum space as an expansion of Mandel's. And also we discussed briefly the features of the modified Foka-Švingera approach. So let us first start with the original Foka-Švingera approach. So basically we have to solve the so-called propagator equation on the left. And it's an equation with the same operator, we call it H, which depends on positions and respective derivatives, with the delta function on the right-hand side, as you can see. So the main idea of the original Foka-Švingera approach is to use the following parameterization using the so-called proper time parameter. So basically we change the task to find an unknown function S to the task of find yet another unknown function U. So what properties should this function U obey? As we can see by substituting this parameterization S into the original equation, we see that the following integral equation should be satisfied. So we're not going into details, the respective details that we found in the original Švingera paper or in some book like the quantum field theory by Itis and Zucker. However, we can check that indeed the solution that you see on the screen satisfies the integral equation, namely the solution is the function U that at the same time satisfies a Schrödinger type equation with following boundary conditions. So let's check. So first, we substitute this function S into the original equation. That's how we obtain right-hand side with H acting on U in the integral. Next, we substitute it with the right-hand side, namely the derivative of the proper time parameter, and compute the integral using boundary conditions, namely like that. And so the delta function is obtained and the solution is verified. So as we know, the solution of this Schrödinger type equation with following boundary conditions could be written in the following form as an exponential operator acting on the delta function. Here we also see that there is a small parameter epsilon which is needed for convergence. So in the original Foka-Švingera approach, they follow an interesting and tricky strategy. Namely, they're trying to use this expression A to reduce the equation B to the form C using the underlying symmetries of the problem. So now let us look at the equations B and C. What is the main difference? The main difference here is that in the operator H, there is a differential operator, dx. However, in expression C, it's just a regular scalar function f, and that's why the equation C is easy to integrate. So once we obtained the equation C, all other things become trivial, while computationally maybe complex, however, in principle trivial. However, this approach has several peculiarities. So first of all, as I said, after we obtained this differential equation of the scalar function, everything becomes trivial, however, resource intensive in some cases. The second feature is that final expression is obtained in the position space. However, in many cases in quantitative theory, we want to use the momentum space expressions. And also, for example, in the case of external magnetic field, the interpretation of this Schwinger parameter is not so obvious, and we'd rather like to use the expansion over Landau levels. So, looking at this integral representation over the proper time parameter of an exponential operator acting on the delta function.
Станислав, sorry, we have a question. We have a question.
Sure.
Not the question, but the statement. But what you mentioned that all the considerations are made in the X space are not the minuses of these considerations, because there do exist the problems when Foka-Schwinger's gauge, Foka-Schwinger modified method was used in X space for the calculation of diagrams. This is not the minus. This is the. Sometimes this is used as the advantage, in fact, because there do exist some examples of the calculation in the X space for the QCD summaries.
Okay, probably yes.
Multiple depths.
Yeah, but in many cases we'd like to use momentum space on low levels decomposition. Yeah, sure. Okay, should I continue?
Yes, sure.
Okay, great. So as we see, during one of the intermediate steps of the original Foka-Schwinger computation, we have this representation of the propagator S as an integral of an exponential operator acting on a delta function. So the question arises, could we directly compute this action of this exponential operator on a delta function problem? And the answer is yes. And so here I would like to present a general scheme of such computation. So first of all, we have to decompose the delta function as a series of integral of the respective quantum numbers, as you see on the screen. Then these quantum numbers are actually the eigenvalues of the H operator, and the respective psi functions are the eigenfunctions of this operator. So basically, one limitation of this method is that we have to know those functions. However, for many interesting problems, we do indeed know the functions in question. So for the first time, this method was presented in the article that is referenced on this slide. And so the computation proceeds as following. So we decompose the delta function as we said before. Next, the H operator acts on the function that depends on x, not on x prime, but rather on x, because the H operator depends only on x. While acting on x, we get the eigenvalue that goes straight into exponent. And now we are left with just an integral over a scalar function of a scalar exponent, which is trivially computed. So, however, there might be additional circumstances, for example, when the H operator is being can be decomposed into parts that compute with each other. And the most interesting case is when this decomposition results in one of the operators, let's call it H0, to have a set of known eigenfunctions. We'll see the examples later, however, in general case, so the decomposition process is follows, and we can sort of split the exponent using the Kэмpbell-Baker-Hausdorffa relation due to the commutativity of these operators. So, so starting from this point, the calculations highly depend on the exact form on those operators. So, in general, we can't say nothing more. Okay, so in the actual PhD thesis, I do present the calculations for the scalar case. However, here I would like to skip it because those calculations would be sort of a trivial result on what's going on next, on what's going to be presented next. So let's go to results. So based on the original Foka-Švingera method for the solution of the propagator equation, I formulated, in general case, its modifications, which consists in representing propagators as an integral of an exponential operator acting on a delta function. This method was applied to find momentum space representations of scalar charged particle in constant magnetic field as an expansion of Landau levels. And also in the PhD thesis, there was made a comparison of three approaches for finding propagators, namely in the canonical quantization scheme and using both the original Foka-Švingera and the modified Foka-Švingera approaches. In the second chapter, I applied the modified Foka-Švingera approach finding propagators for particles with spin, namely for fermion and for nested vector boson. I also report another paper that was published by a different group who used this method just after 1 year of its original publications, and they used this method to find the propagator of electron in the rotating environment. So let us start from the most interesting case, namely the propagator of charged vector boson in magnetic field. This case has the most mathematical richness because of underlying symmetries and other features. So the equation to find propagator for the massive vector boson in arbitrary psi gauge is presented on this slide. So here we can see that it consists of basically three parts. First part, it sort of describes the propagation of scalar particles. Second part can be attributed to the interaction of the particle of the particle's spin with the magnetic field, and the third part responsible for the arbitrary psi gauge. So the magnetic field is encoded into a field tensor that you see on the right with the cavalier derivative and the four potential chosen as presented. Now let us notice that operators A and B do commute. However, A and C and and B and C do not commute. But there is a nice relation which allows us to simplify computations during this exponential decomposition step, namely that the sum of operators A and B does commute with C. So now let's use it. So according to the modified Foka-Švingera approach, we have to write the propagator as an integral over the exponential operator acting on the delta function. So this exponential operator consists of three parts, as we already know, A, B, and C. And now let's separate the exponent using the commutational relations. So first of all, the sum of A and B commutes with C. So first we separate out just the C part. And now we can, we are left with just A and B, which do commute. That's why we can separate the remaining two operators. And so we have the composition of the exponential operator in the following order: first C, then B, then A. If you would do it in any other order, it might not work because of the computation equations. So let's see if one of the intermediate expressions. So what we see here is kind of a nested structure, like Russian dough. So first, there is a delta function which is being acted upon by an exponential operator which corresponds to the propagator of scalar particle. Next, another operator acts on this result and accounts for the spin. Actually, we would see the following structure if we considered the problem of finding the electron's propagator. But as I said, the case of vector boson in our precise gauge is more mathematically rich because there is another term with another exponential operator which accounts for the arbitrary psi gauge. Now comes a question about delta function decomposition, and it so happens that the operator that we might call H0, the one you see in red, namely the first exponent, it has known eigenfunctions, and so that's why we can decompose the delta function in the following way, where the t, z, and y components are just regular complex exponentials, plane waves, and the x component is described by quantum harmonic oscillator eigenfunctions, dm. And using this decomposition and the eigenvalue relations, we can apply this operator in the exponential to this delta function decomposition to obtain the corresponding eigenvalue, for example. So the next exponent is the exponent which has tangent.
Can you show previous slide?
Yeah, sure.
You don't integrate over tau yet, right?
No, not yet.
Okay. Okay, go ahead.
Okay. So the next exponent is an exponent which has field tensor, and provided that the field tensor expression is simple, it is easily evaluated and decomposed into two parts, namely the so-called parallel part, which is basically a part which contains t and z components, and the perpendicular part, which is oscillatory with cosines and sines. And finally, the third exponent, which depends on psi, it's it's also not very hard to evaluate, and as you can see, it evaluates into the sum of just a particle delta, which corresponds to the choice of psi equals 1, and also a term which is sort of a correction for psi values that are different from 1. And as we see, no exponents are left. So with both the first exponent we obtain here in the red, the scalar value. Here we obtain just matrices or tensors if you like. And finally, here we obtain a linear expression with maybe a fraction with p squared in the denominator. However, it's not a big problem here. And as you can see, using each term, we can with each term we can use the eigenfunction eigenvalue relations which are associated with this problem. And that's how we can proceed with calculations easily and with less effort than in the original Foka-Schwingerera approach. So, well, despite the fact that this modified Foka-Schwingerera approach provides some shortcuts to overall computations, however, some other transformations are not that trivial and require some computational effort, and I will not provide them here. But basically, just after a few steps from this step, the proper time integral will be evaluated. So that's the main point. So let me provide the final expression with propagator. As you can see here, this is a Fourier image here, Fourier image which is basically a Landau level decomposition of the propagator. It consists, as we see, of three parts that were present in the previous slide. So the green one, the blue one, and the red one. So the red one is the part that is sort of a propagator of a scalar particle. However, for scalar particle, there will be different. The summation will start from 0, as far as I remember. The second part here, the blue one, corresponds to the spin exponent and describes the propagation of particle with spin 1 when psi is equals also to 1. And the second part describes the part that is attributed to the arbitrary psi gauge. So that's basically the result. It was published in PhysRevD a year ago, I guess. Yes. And in 2020, yes. Okay. So let's come to results. So first of all, there was obtained a representation of massive vector boson propagator in arbitrary constant electromagnetic field. Namely, here, let me show once again. And this formula on top, this tensor f mu rho, could be an arbitrary electromagnetic tensor, not just describing the constant magnetic field, but however any constant electromagnetic field. And so this representation was obtained as an integral over the proper time parameter, and under this integral there was a set of three exponential operators acting in a sequence on a delta function. And also there was obtained a momentum space representation for particles with spin, fermion, and vector boson in constant magnetic field as an extension of Landau levels. Let me make a few remarks. So first of all, why the modified Foka-Schwingerera approach is useful compared to the original Foka-Schwingerera approach or to the canonical quantization scheme. So actually actually, I made a few comments on the comparison with canonical quantization scheme. And if you compare it with the original Foka-Švingera approach, we see that in order to obtain the desired momentum space Landau level decomposition, which in many problems is very useful, we have to do it in several steps. So first to obtain the position space decomposition using the Švingera parameter, next to transform into the momentum space, and next to transform from the Švingera parameter to the Landau levels expansion. However, using the modified Foka-Švingera approach, we could obtain the desired result almost directly in the momentum space. We will just have to do a tiny bit of integrations to go from the remaining position space coordinates to momentum space coordinates. We'll see it also in the following chapter. And the second remark is quite curious. When describing processes in curved space, we use actually the same mathematical approach, namely the covariant derivative formulas. And it turns out that the modified Foka-Švingera approach could be also used, and probably the original Foka-Švingera approach for sure, but it could be used also for this type of problems. And so actually we have a confirmation that of successful application of the modified Foka-Švingera approach for the problem of finding the propagator of the fermion in a rotating environment. So basically for a problem of finding propagator in curved space. Or to be more precise, using curvilinear coordinates, to be more precise. So I will not present the details of this paper. However, the main ideas was to consider the following crystal symbols and geometric tensor, to construct the connection symbols gamma, and then to pass to this quadratic equation, to go from the original quadratic equation to quadratic version of the equation and find the general form of functions phi. And then, as was presented in the introduction to the modified Foka-Švingera approach, once we have the general form of the solution, we can next use it. We can next construct the delta-function expansion using the normal relations. And that's how this group of actors proceeded, and they successfully obtained those results. Well, the results are tremendous in size. So I'm just showing the main idea that the approach can be used elsewhere.
Да.
So.
Okay, so now the final chapter. The final chapter concerns the position space representation of those propagators. So, as I previously told, the majority of problems in quantum field theory, in one way or another, may rely on momentum space representation of those propagators and field functions and everything. However, there are some cases where position space expressions have some advantages. For example, in the calculation of sunset type diagrams. So you see a reference on the screen. So, and also, it is nice that we can also apply a variety of regularization techniques to treat infinities in those blue diagrams using position space representation propagators. So all of this motivates not to consider just momentum space representations of charge particle propagators expanded all Landau levels, but also their position space counterparts. Okay, so this chapter I present the position space expressions expanded all and down levels for scalar fermion and vector Boltzmann particles. And particularly for the scalar particle, I present derivation using all three methods, namely the original Foka-Švingera method, the canonical quantization approach, and the modified Foka-Švingera method. Great. So let us look at the expression to start with. So this expression comes from the application of the original Foka-Švingera approach to the problem of finding the propagator of scalar particle in constant magnetic field. Relevant details can be found either in the original Schwingera paper or in the quantum field theory by Inzit and Zuber, or in the text of the PhD thesis. To start with, I present just the final result of the propagator written as proper time integral in position space. So let's try and convert this integral over the proper time parameter into the expansion of one doublets. So first of all, we can note that the integral on the top it resembles the known relation for one of the Bessel functions, namely k nu. It's McDonald function, as far as I remember. So relevant parts are colored like this red part corresponds to this red part, and this green part corresponds to that green part, and so on. So using the following substitution, we could transform the parts of the integrand, according to the following. And on this line, we obtain an expression that actually resembles the generating functions for Laguerre polynomials here. So this allows us to pass from this exponential expression actually to the series of a bunch of terms which will eventually come out to be Landau levels. And so, as you can see on top, if we also name yet another substitution, namely this one, it will result in the following expression with an integral over the proper time parameter. And this integral is actually a well-known representation of this k0 function. And that's how we obtain the solution for the propagating equation for the case when the interval is space-like. So if we now use the standard relations of Bessel function, we can also transform this k0 function for space-like integral to this h0 second function for the time-like integral to obtain the final solution for final expression for the position space expression of the propagator expanded over the dot levels. And also here I reference our paper, which concerns this result.
And excuse me, what was the conference where did you report this?
It was in MIFID. It was in MIFID, the conference on particle physics and actual physics, I guess. It was called International Conference on Particle Physics and Astrophysics. I participated twice in this conference in 2018 for the original, the original results with modified Foka-Švingera approach, and in 2020 with the results for position space representation. Should I continue?
Yeah, sure.
Okay. So now let's try to obtain the same results, however, this time using the modified Foka-Švingera approach. So now let's go briefly through the remaining ingredients of the method. So first of all, we have the corresponding propagator equation here. Next, we know from the modified Foka-Švingera approach that the answer to the given problem is written as an integral over the exponent acting on the delta function. We also know the decomposition of the delta function as follows. Now we can apply this exponential operator to this decomposition using these eigenvalue, eigenfunction relations to get the expression on top. So it's expression on top. Now we see that this expression is not symmetric. So what do I mean by symmetric? Here we have part which is sort of which sort of describes the propagation of a particle in one plus one dimensional Minkowski space. And also we have terms which are sort of not symmetric in the xy plane. Because here we have an exponential which depends on the y coordinate, and those quantum harmonic oscillator eigenfunctions which depend on x coordinate. To make this expression symmetric, we can integrate over py parameter. So once again, these etas and eta primes, they actually do depend on py and py prime, and so that's why we have to integrate also those functions, like you see here. So once again, this integral is known, and it is tabulated in reference books. So here I just provided the final answer for this integral. And also please note that there is a not invariant base factor, which is common for this type of problems, and we get it during this step, during this integration. So now you see that apart from this non-invariant phase factor, we obtain a sort of symmetric representation of propagator. It is symmetric in the xy plane. It actually has radial symmetry that is actually inherent to the problem. And in the tz plane, it describes the propagation of 1 plus 1 dimensional of a scalar particle in 1 plus 1 dimensional Minkowski space. To get the full position space representation, what we have to do is just to evaluate this integral, which is also an odd integral, and the results are presented here, both for space-like and time-like integrals. And so the final expression is once again the same that we've seen using the original Foka-Švingera approach. So both methods show high degree of consistency, and also the canonical quantization schemes is also consistent with this result. The calculations of respective propagators for fermion and massive vector boson are much trickier. However, they follow the same general rule of first applying the modified Foka-Švingera approach and doing these kind of integrals that you see here. So, however, a slightly more difficult integrals with some more features present for these functions. However, all these integrals are quite doable and also are tabulated in reference books. And during this presentation, I just provided the final results from our paper that you see referenced here on the screen in European Physical Journal C, that was published just a few weeks ago. So, and our result is for massive vector goes on. So all those expressions are quite huge. So I just present them as is with no derivation. So going over the results of this chapter, I would like to say that in this chapter there was constructed position space representations of propagators as a decomposition of Landau level for massive charged particles such as scalar fermion vector boson in quantum magnetic field, and also for the scalar particle I considered all of three methods which I discussed in my PhD thesis, namely the original Foka-Švingera approach, the canonical quantization approach, and the modified Foka-Švingera approach. And the results were consistent among all of those three methods. And actually, what was not shown here is a couple of slides where we discuss properties of the position space representation, namely the interaction between the radial and parallel terms in this decomposition. Let me show you. Between this term and this term, there is kind of an interaction that is governed by the Landau level number n. However, as of now, I do not discuss it. However, this also be found in the PhD thesis. So the main results were presented in respective chapters. However, let me briefly go through the main conclusions of this work. So there was developed a modification of the original Foka-Švingera approach for solving of the propagator equation. It turns out that the modified Foka-Švingera approach it has some advantages over the original Foka-Švingera approach and also over the canonical quantization scheme, allowing to reduce the computational complexity and also to find additional representations of propagators. Using this modified Foka-Švingera approach, I obtained both position space and momentum space representations of charged particle propagators, scalar fermion vector boson, in constant magnetic field as an expansion of Landau level. In the particular case of massive vector boson, using the modified Foka-Švingera approach, I obtained a general representation of the propagator in arbitrary constant electromagnetic field, as was previously shown. I also studied some properties of position space representation, namely, which I call an interaction between radial and parallel factors in the decomposition. So it is presented in PhD thesis. And last comment is that this modified Foka-Švingera approach, as well as the original Foka-Švingera approach, they can be used to construct propagators not just in such conditions as external electromagnetic fields, but also in curved spaces and curvilinear coordinates, which is due to the same mathematical formalism of covariant derivative, which was independently confirmed by another group of scientists who published the paper that I commented on. Thank you for your attention.
Thank you, Stanislav. We have time for questions.
Yeah, sure.
Probably some questions from... Oh. So...
You could go on Russian if you want.
Is it planned to use these results in any concrete calculations? Because it's in fact on the first transparency you have written down the Feynman diagram. I guess 3 loop.
Which slide? Which slide is it?
On the first slide.
On the very first
The
slide.
very first line.
Zero.
Zero.
The second.
No, the zeros.
Oh yeah, it's just a picture, but actually we have plans to apply this position space results for loop diagrams, but not yet. This particular work is more or less theoretical, sort of, but actually we do have plans to apply those results. Yes.
Which of your expressions have not been known beforehand? Which are new?
Actually, some of the expressions were known previously. For example, for position space, momentum space representation of an electron, and also in a different form, momentum space representation for W boson. However, all of the expressions for the position space representations of the double levels were not known previously, and those are new results. And some of the representations in the momentum space are also new results. For example, this general form I report here is a new result. It was not known previously. And also the properties that I indicated. The properties of the position space representation that I indicated in the results and are not presented here. They actually presented in the PhD thesis, and they also new.
Okay, more questions?
One formal question. Can you show the list of papers which are, on which your thesis is based?
Do you mean my papers with my participation?
Yeah. Which are
okay. There is no a list. However, I can slide through this presentation, like over this presentation, and find them. So the first paper was in 2019, where we introduced this exponential operator approach that we called it those days. So it's modified Foka-Švingera approach. Next, there was a paper in physical review D that we obtained all of this representation for the massive vector boson in arbitrary psi gauge in cosmognetic field. The next paper is also a conference paper in the conference journal, which concerns this scalar case for position space expression expanded over and over levels from a scalar particle. And the last paper, which was published just recently, concerns the application of all the methods for the scalar case, and also the application to the fermion and vector boson cases. So it was published in European Physics Journal C.
Any more questions? Probably questions from people participating via Zoom. Well,
I have one more question, more technical. There is a big difference, appears to be a big difference between static electromagnetic fields of electric type and magnetic type, meaning that you can sometimes make a Lorentz transformation to cast the constant electromagnetic field into pure magnetic field, and sometimes you can't. So is there a major difference in the expressions for the propagate in this case?
I'm not sure. However, I've seen a general expression for the propagator of W boson in constant electromagnetic field. I think with electric and magnetic fields being perpendicular to each other by Nicky Shaw. There was a paper by Nicky Shaw. And as far as I remember, some kind of standard functions we use there to describe the propagation, and all the results looked kind of the same. But I'm not sure, because in this particular work we mainly concern the constant magnetic field case, because it is one of the easiest cases to analyze. However, there are definitely plans to study different setups. For example, charge particle propagation in plane wave background, and so on.
Okay. So may I ask you a question? What about practical applications of your method? Because if you have big electromagnetic field, you can use perturbation theory to calculate propagator, for instance. So it means that the effects of your method will be important for rather strong magnetic field. Correct? So what about practical applications? So it seems to me that it could work rather well for very strong magnetic fields, or I'm wrong?
As far as I can tell, the applications of this method, the modified Foka-Švingera approach, are basically the same as the original Foka-Švingera approach or canonical quantization approach in some cases. The approaches I presented, it just gives us some computational shortcuts by simplifying the calculation. However, there is a possibility that representations, the general forms of representation like this one, could give us some advantages by maybe using power expansion of respective exponents. Within the perturbation theory approach.
But the question the question was how strong is your magnetic field, which is you considering. Is it really very strong, or it is not very strong and may be used within perturbation theory considerations? And what are the possible physical, where these results in physics may be used?
Well, the types of magnetic fields that can be considered using this expression are basically the same types and strengths of magnetic fields as for any other methods. So, for example, here for the W boson case, we see that that this summation starts from n equals to -1. Therefore, at some point in time, therefore, for some strengths of magnetic fields, leading to so-called vacuum instability. So that's why there's a kind of initial boundary of magnetic fields that can be considered. Now, speaking of the application of such expressions, so for example, those propagators are usually used for calculation, let's say, of the self-energy for neutrino, for example, or in other astrophysical setups.
Okay, more questions? I didn't see any, so let us thank the speaker. Thank you very much.
Thank you.
Спасибо. Станислав, а вы когда собираетесь подавать документы?
Вот, это хороший вопрос. Это можно сейчас обсудить с вами?
Ну, можно.
Ага, ну, смотрите, я сейчас нахожусь в рабочей поездке, вот. А в связи со всей этой ситуацией, как бы, ну, вот, непонятно, когда я даже вернусь.
А у вас зарубежная, да, рабочая поездка?
Что говорите?
Зарубежная рабочая поездка?
Да, зарубежная.
А, понятно. Смотрите, ну я вам сроки обрисовал более-менее, правильно? У нас...
можно еще раз проговорить, чтобы точное понимание было, когда, вот, смотрите, можно я вопрос задам?
Да.
Когда последний день осени, весны, когда я могу подать?
Это мне будет сложно ответить на этот вопрос.
Хорошо.
Потому что я не знаю, кто еще будет подавать и когда мы сделаем заседание диссертационного совета. Значит, смотрите, ближайшие 2 заседания диссертационного совета у нас, собственно, в середине апреля. Там в общем, у нас заседания обычно по четвергам, если они есть. И это там то ли 14 и через неделю. Это ближайшие 2. Соответственно, когда...
21,
ну да, когда-то там, значит. Это в апреле. А насчет того, будет ли в мае, я не знаю. В июне точно одно запланировано, потому что там защиты будут. 30 июня. В принципе, если мы примем вас 30 июня... Ну просто, значит, смотрите, если кто-то до вас много подаст, если до вас много подадут заявления, мы просто физически не сможем обслужить такое количество, как говорится, диссертаций, понимаете, да? Но если их будет немного, то успеем.
Каковы ваши ожидания?
Ну, вот смотрите, сейчас подано 4 заявления. Две диссертации, одна диссертация, точнее, уже назначен срок, вот на 30 июня. Еще будет 3, значит, из тех, кто подал уже. Это, соответственно, 2 из них попадут на 30 июня, а 1 попадет на сентябрь. И я знаю еще о 2, наверное, кто будет. Это означает, что, в принципе, в сентябре у нас 3 защиты. При хорошем раскладе это 1 день, но в сентябре, в принципе, мы планируем 2 раза прозаседать, поэтому, в принципе, вы можете вполне попасть.
Вот для меня идеальным был бы вариант как можно позже сейчас подать и как можно позже, ну, до октября, то есть в сентябре, защититься.
А почему как можно позже? С чем так связано это?
Ну, вы же понимаете, ситуация сейчас нестабильная, как бы.
Нет, я понимаю, то есть вы просто в России не появитесь, да, в этом проблема?
Ну, вот, скорее всего, в этом, потому что мне даже пришлось как можно раньше ехать. Мне и так эта поездка планировалась, просто она сместилась на 2 недели раньше. Вот.
То есть у вас сейчас даже планов нет, когда вы вернетесь, правильно я понимаю?
По всей видимости, да. Не буду вам брать.
Ну, в общем, я вам примерно все обрисовал, значит...
Да, ну да.
То есть если 30, например, июня мы вас примем, в принципе, в сентябре защита возможна. Потому что там должно 2 месяца пройти, вы должны успеть там разослать автореферат и так далее. Вот за это все, за 2 месяца до защиты, соответственно, если 30 будет принятие, то в сентябре, там какого-то числа, вполне можно организовать защиту. Еще раз повторяю, если за это время никто не займет, как говорится, ну мы же работаем по заявлениям. Если кто принесет раньше заявление, соответственно, мы будем организовывать раньше.
В общем, я приложу все усилия, чтобы сделать это как можно раньше, и буду надеяться, что все будет хорошо. Вот. Ну, в любом случае, я прилечу, если там совсем надо будет делать, я постараюсь.
Понятно. Хорошо.
Да, в целом, то есть, есть ли какая-то бюрократическая формальность по оформлению вот этого семинара, то есть, я какую-то бумажку получить должен о том, что я участвовал на семинаре, или вот.
Ну, в принципе, формально нет. От нас даже... Ну, раньше мы это делали иногда. В принципе, сейчас даже не делают это.
Ну, хорошо, да, хорошо. Ладно, спасибо большое вам.
Да нет,
можно, в принципе, Сергей? То есть заключение вот о семинаре не пишется сейчас?
Ну, как-то мы в последнее время...
Раньше писали.
Ну, раньше мы писали, но это было, во-первых, это было не обязательно, ВАК это не требует. Это документ, который мы прикладываем, ну, он внутри остается, грубо говоря, мы его даже в ВАК не отправляли никогда. Вот. В принципе, если хотите, можете написать. Ничему это не будет противоречить. Я могу вам образец прислать, а может быть у вас есть образцы от предыдущих наших, ну, ваших, точнее, коллег, которые у нас защищались. Я могу прислать какой-нибудь такой образец, чтобы...
Да, если не трудно, да. Потому что где-то года полтора защищался у нас Шленев в вашем совете.
Да. Угу. А, кстати, на Шленева, по-моему, мы не делали как раз. Уже не делали.
Уже не делали, да.
Нет. Поэтому до этого, наверное, там Дмитрий Румянцев, может быть, кто-то еще. Ну, я посмотрю, у меня, наверное, остались. Хорошо, я пришлю тогда, Станислав, вам.
Большое спасибо.
Все, какие
тогда
вопросы?
Будем надеяться, что все будет хорошо.
Да, конечно. Угу. Связывайтесь по поводу всяких формальностей, формальные документы и так далее. Связывайтесь с Анной Александровной Бреевой. По-моему, я вам давал ее контакт по электронной почте.
Анна Александрова, да?
Да, она принимает у нас документы.
То есть это нужно лично все оригиналы бумажки, да?
Да. Ну, точнее, что-то можно удаленно, так сказать, а что-то надо в какой-то момент очно там приехать и сделать.
А если я, допустим, начну эту процедуру, в любом случае требуется оригинал распечатанной диссертации, да, или PDF недостаточно?
Да, в любом случае первый этап это диссертация. Ну, смотрите.
Хорошо.
Ну да, потому что это все начинается с диссертации. Она грузится на сайт, и вообще-то все начинается с того, как вы приносите оригинал диссертации, более-менее.
Все понял, да, все понял. Все? Спасибо большое, да, еще раз. Я думаю, у меня больше вопросов нет.
Ладно, хорошо. Угу. Нет. Все, спасибо.
Да, Сергей, еще вопрос.
Да.
Присутствие оппонентов. Обоих обязательно на защите или можно будет кого-то удаленно, например, послушать кого-то из оппонентов?
В принципе, кого-то можно будет удаленно послушать, да. Один желательно, чтобы был.
Один личный, один можно удаленно.
Да, значит, в принципе, если у нас если будет организовано вообще, сейчас есть такая опция организовывать диссовет в то, что называется дистанционно удаленный режим. И в этом случае все оппоненты могут участвовать удаленно. Но я не могу гарантировать, что именно в таком режиме будет проходить заседание. А если
не в таком, то одному оппоненту можно удаленно.
Да, если не в таком, то лучше одного оппонента, чтобы он был, а второй, так сказать, может быть удаленно.
Хорошо, спасибо.
Не за что.
Ага, отлично. Спасибо, до свидания.
Ладно, все, до свидания.
Всего доброго.
Были рады вас заслушать.
Тоже очень.